larger size scale, that's not the case. Another interesting phenomenon that relates to this is the fact that the sidewalls can actually carry some of the load. In a fluid, that basically is not the case. If you take a cylinder of fluid and you put a pressure sensor on the bottom, as you fill the cylinder up, the pressure on the bottom increases more and more, linear. Put in 3 feet of water, pressure goes up so much. Put in another 3 feet, it goes up that much again. This continues almost indefinitely because water is fairly incompressible. You go to the bottom of the Marianas Trench in the South Pacific Ocean, 7 miles underwater, the pressure is massive there. It's still pretty much linear. The water there is about 3% more dense than on the surface. And it's under thousands of tons per square inch of pressure. So a fluid has this very simple linear relationship between depth and pressure. In a granular material, nothing at all like that. At first, the first grain that I put in this container, all its weight will be on the bottom of the cell. As I add more and more, they get spread out, and eventually the sides start carrying some of the load. If I increase this container 5, 6, 7 diameters up, most of the load of the top particles will be carried by the sidewalls. One of the experiments I built early in my graduate career, you take a cylinder, go back to the board here. I like using both overheads and the board, and wish there was one nearby. So if you take a cylinder, where you have the sidewalls here, and a bottom here, and they're disconnected, so the sidewalls have some sort of support structure like that, and make the bottom into a scale. I'm drawing just sort of a grocery scale, but literally you put electronics under there, and make sure this gap here is smaller than the radius of the particle. You can add particles to this, fill it up with grains. You get the idea. I don't want to draw 100 circles. If you fill it up with grains, if you put in 500 grams of grains and then fill it up and say it goes up to about here, you'll find that the weight on the floor is about 300 grams. And 200 grams are carried by the sidewall. But it gets more interesting. All these force chains are very small contact points. And it's governed by the exact geometry of the material in the shell. So if you build this thing and set it up, and then you just take your hand and put it around the outer cylinder, and these particles inside are something like brass, so they conduct heat pretty well, the heat of your hand is enough to cause thermal expansion to change the network of force chains. And you can see the weight that you measure on the bottom go up or down. For 500 grams of material, you could get weights as high as 700 or 750 grams if the sidewalls end up pushing down, and weights as light as 100 grams or less. And so you hold the thing, you warm it up, the weight usually goes up because the particles are expanding and getting pushed in more directions. And then you let go, it cools down, it goes back to the weight it was before. Grab it again, warm it up. And when it's warm, if you just tap the side of the container, it sends a shock wave through that releases some of these tensions. The particles rearrange, the force chains rearrange. It goes back to about 300 grams. And then as it cools, the force chains change again and the weight drops down. So the mass you measure on the bottom plate can vary tremendously. It's a great demonstration. I want to build it someday, but it's involved and requires a lot more parts than I have time to assemble over a couple of weeks. Question?
Does this apply to granular, like only grains or any type of solids?
Well, this is a particular property that's unique to granular materials. A solid block of metal would have the same mass no matter what. If I put a fluid in there, the mass I measured on the bottom would be the same, and it would be the full weight of the fluid, provided there was no flow going on in the cylinder, so there would be no hydrostatic forces or Bernoulli issues going on. But yeah, this is unique to granular materials. And in fact, that's one of the reasons why grain silos are built the way they are. They don't have to be strong enough to carry all the weight of the grain at the very bottom of the silo, because the sides do some of the work. But if a farmer overloads their grain silo, then it'll rupture, and usually the sidewalls fail, and you just get a big mess. Yes?
So will the shape of the grain influence the behavior?
Yes, force chains are definitely a function of the shape of the force chains. The force chains are definitely partly a function of the shape. That's one of the things that matters. Oblong grains have different force chains than spherical grains or roughly cubical grains.
But are they predictable?
In what sense?
Well, for the ball, you can predict, if you put it there, I guess you take photographs, and it will repeat.
It's roughly predictable, but given that it's a function of the particular configuration of the grains, it's sort of statistical. You know, you get a range that you expect.
Right. But for the
roughly,
round balls, and then for the cubes, we'll have another behavior, and
you can predict similar behaviors and the characteristic behaviors to different shapes. There are a lot of other factors, though. You know, the surface roughness makes a big difference. Density matters. The thermal expansion, response to pressure. There's a whole bunch of microscopic properties that change these things. So typically, someone will take one material and work with it, and then change one or two things. Changing a lot of things can be a real mess. So there's another nice thing you can do with these changes is that after that period. Okay, apologies there. If you look at the printed notes, please put a dot right there. Right. They're photoelastic materials. Those are materials that when light goes through them and they're under stress, they change the polarization of light. And one common experimental technique in this field is to take these photoelastic materials and cut little discs out of them and make a two-dimensional system of grains. And then you put a polarizer in one direction on the back and a polarizer in the other direction on the front. And then everything will look kind of dark. And then as soon as there's pressure on the grains, they start rotating the light, the polarization of light, which allows it to pass through both polarizers and look lighter. So you can actually measure where the stresses are and see the force change, visualize them directly by that. And I think the next slide, yes, is one of those. This is from Bob Behringer's group at Duke. I actually put the reference to his homepage, and you can look it up yourself if you want. Tilde Bob is, he's a really casual guy. So this is, you can see here, these are the particular particles. And you can see they're not all the same size. If they're all the same size, you tend to get crystallization effects, so people avoid that in this kind of experiments, particularly in 2D. It's less common in 3D. And you can see that the bright areas are places where there's a lot of force. And if you look very closely, you can see there's little dark patches here. What actually happens is the rotation of the light is a function of the stress on the particle, and as there's more stress, it can rotate it 90, you get full brightness. At 180, you get dark again. So by counting the fringes, you can actually measure quantitatively measure the stress on these particles. It's a little more work to do, but for our purposes, the light regions have more stress, and you can see the force chains that are built up in this material. This is part of a larger cell. I think Behringer's work, he used a cylinder, an annulus between two cylinders, and rotated one of them, and various other things, and watched the flow as the grains move. But you also notice there are chains that are big areas that are almost empty. Right here, this cell of 4 particles have basically no stress at all on them. Here's another group that has very little stress. And then there's some here, you can see there's a lot of stress there, and lines there. And if we move these particles around, this network will change completely. You know, these 4 particles might be carrying a huge load, and then there might be nothing right in here, which by changing configuration, it's just a small amount. So the movement of these things is interesting. I did some work when I was, over the summer of 2005, I went down to do a project in Chile with one of the people I'd done other work with. And we built a rig to do this sort of experiment. Here's a picture of it. The idea of ours was that this slide here, to start, both of the borders here and there are roughened with particle-sized cutouts, half particles that are just glued on, different sizes spaced along there. There's little bumps on the bottom to give it something to grab onto. The middle is filled with a photoelastic material, and we view it through cross-polarizers. And this wall here is free to slide up and down. The purpose of that was to keep the system at a constant pressure, effectively. For the grains to move, they need to shift and move over. There's a phenomenon called Reynolds latency, which you'll see when I show the video, if I can get the video to work. I tried it with things on my computer, and it wasn't able to, but I've got the videos on the files, so we'll see if we can go to that next. But as they move, they require some space to shift over each other, so you have to have room for expansion. All the other experiments in this arena that have been done were done in fixed volume, so the particles had to compress themselves in order to move. And I wanted to create one of those a constant volume flow and a linear shearing, a model that it's limited. We can't do it forever. In a spherical circuit, cylindrical, you can spin it, spin it, spin it as long as you want. This way we can only shift it a bit and then just stop and go back the other way. So we get limited results. But what we're looking at was the startup process and how the fluidization happened, going from static with some force on it but not moving to starting to move. And we could easily explore that with this rig. Now let me try and let me get out of here and show you the underworkings now and do this stuff. And let's try and just minimize this. See if I can get the videos to work. Graphics. Alright, let's try this. I wanted to show up 10 minutes early and get this tested out. I didn't have time.
Yeah.
Sorry.
Let's see if you say recommending settings.
Here we go.
Let's see if we... There you go.
Connecting. Yeah, excellent. So that's what it looks like when it's in motion. You can see the force chains moving and changing as the particles move. A way to tell it to play over and over again?
Yeah, just the play, yeah.
There we go. So we'll let it cycle. So that's what the experiment that I've built does. This is what they look like in motion. The force chains move around. And you can also notice that when the particles are moving this way, the force chains tend to go like that. When the particles are moving this way, they tend to be in this direction. They're sort of resisting the motion. So the slope of those changes is a function of the direction of motion. It changes as you go back and forth. This is just one cycle looped. So you're not going to see anything different, but you can see the motion over and over again. And you can see that sometimes there are parts that have virtually no force chains at all in them, like here they said it's be quiet for periods. And then other times, right now that, let me shift it back, that side got quieter. So about now, this side gets pretty dark. And over there. So that's the actual forces visualized. That's what's going on in the granular bed. Okay, I'll see if I can get the other one going. One other movie, it's basically the same idea, different example of the same stuff. So that one takes longer to learn. Oh, it's bigger. So again, same idea. As they move back and forth, force changes shift around and change. You can also notice that the top wall is bouncing up and down a little bit. If you put a finger on it, see it moves a tiny bit up and down. That's the Reynolds dilatancy. As the particles move, they need extra space. They push up on the wall. The wall had a constant small force on it. We literally took a string and over a pulley and hung a weight on the end of it to provide a fairly constant force, just the force of gravity on that weight pushing the wall inward. You know, the string had a pulley in here and then a pulley that fall over the other end. But okay, enough of that. Let's get back to the main talk, view, full screen. I apologize for the technological issues. It would have been nice to put it right in the presentation, but I haven't figured out how to do that with LaTeX. So there's a way. I need to download the new movie package and some other stuff that I didn't know how to do it. I'm figuring it out. I'll get it eventually. Okay. We also talk about the idea of a configuration space. The exact position of each grain and the contact force of neighboring grains form what's called a configuration space. You can look at each grain's position as being a dimension in that position space. A simple example of this would be, take a simple pendulum. It has basically two parameters that we can talk about. If it's a one-dimensional pendulum, a simple stick and a mass. It can have some position theta and some velocity omega. So we draw a graph in 2 dimensions. This is theta and that's omega. So the angle it's at and the speed it's moving at. And those graphs for a pendulum tend to be ovals. So this point here would represent sitting in the middle. Theta is positive. So this would represent the extreme end here. where theta is large and positive, say over there, and the velocity is 0. This point would represent the middle, moving that way. Velocity is negative, or angular velocity is negative, and the position is 0, and so forth. And as the pendulum rocks back and forth, it goes around in this configuration space on this oval. If I give